Welcome to the lesson on chemical equilibrium. This lesson is part of mass transfer, which is being taught as part of the NPTEL MOOC on transport phenomena in materials. The objective of this lesson is as follows. During mass transfer, we need a constitutive relationship for diffusion. We need to identify the reason why species diffuse. And by determining the conditions for equilibrium between two phases, we hope to see the reason why the species diffuse. So deviation from equilibrium is then deemed as reason why species diffuse. So the assumptions for us in making this derivation are as follows. So we consider two regions, one region which is basically phase alpha, second region is phase beta, the blue and the green color regions respectively. These could actually be two regions of the same phase too, and we consider that the system is comprised of these two regions, and it is shown here as the maroon box, and we consider this system to be isolated from the surroundings. So the phases that are considered are alpha and beta. The system, which is the box colored in maroon, is thermally isolated from the surroundings, and the system has a rigid boundary. What it means is that we do not have any work that is being done on the box. There is no volume change in the box, and we consider the system to be inert, which means the species in the regions alpha and beta do not change. And we also assume that the interface between alpha and beta is flat, which is being shown here. This interface between them is flat, and we realize at this stage that extensive variables are summative, which is what is going to be used to write Gibbs energy or entropy, which are extensive variables, for the whole system as a sum of what is the quantity for alpha and beta respectively. So let us start by writing the entropy of the system. So we can write the entropy of the system, which is the extensive quantity with a prime on it, S prime cis, and we can see that it can be written as a sum of the entropies of the regions alpha and beta, and therefore any change in the entropy of the system can be seen as the sum of the changes of the entropies in alpha and beta regions respectively. This is within the system, and we can write the internal energy of phase alpha as follows. U alpha, which is the extensive variable, written as a function of entropy, volume, and the number of species, number of moles of species I in alpha. If there are C number of species, then we consider this variable to be going from I is equal to 1 to C, where C is the total number of species. We can similarly write the internal energy of the phase beta in the same manner, and we can combine the first and second laws to write the following expression for the alpha, which is du is equal to TdS minus PdV plus the chemical work, which is the chemical potential mu times dNi, the number of moles that are changed in the system, and because the total number of species is C, we have a summation over the entire number of species here. So similarly we can write the internal energy of the phase beta in the same manner. So we can then look at these expressions and rearrange the terms. So what we want is, we want this term to be on the left hand side. So we do that rearrangement. So we do that rearrangement of making the entropy term on the left hand side, and it can be written as follows here, as you can see here, and similarly it can be written for beta phase also. So ds prime alpha is du prime alpha by T alpha plus P alpha by T alpha into dV alpha minus summation of chemical potential alpha for the species I by temperature of alpha into dNi alpha. Similarly for the beta. And we can then sum it up as we have seen for earlier. The change in the entropy of the system is the sum of the changes of the entropy of alpha and beta regions, which is then written here. This is for the alpha region and this is for the beta region. So once we have these terms, we just then gather the terms that have the similar appearance. So before we do that, we derive some quantities that are useful. We know that the internal energy of the system is going to be not changed if the system is thermally isolated. The reason being that internal energy of a system can only be changed either through heat or through work. And when we said that the system is thermally isolated from the surroundings and also that the system is enclosed in a rigid wall, we say that this basically that there is no heat that is being given to the system and there is no work that is being done on the system. So therefore the internal energy of the entire system should be constant, which means that the change in the internal energy must be 0. And this change in the internal energy is written as a sum of the internal energy change for alpha and beta, which means that du alpha plus du beta is equal to 0. This means that du alpha is equal to minus du beta. Now this is a relationship that is very important for us because we are going to use this to eliminate one of the two quantities. Similarly, because the system has rigid boundary, the volume of the entire system is not going to change. So we can say that V system is equal to constant, which means that the change in the volume of the system is 0. And again, the volume of the system is taken as a summation of the volume of the alpha region and the volume of the beta region, which means that the change in the volume of the alpha region plus the change in the volume of the beta region is equal to 0, which means that dV alpha is equal to minus dV beta. Again, this is again a important relationship for us because we are going to use this to eliminate one of the two quantities that are listed. And because the system is actually isolated, in other words, there are no atoms or species that are going to enter the system or leave the system. This means that for every I, so this equation is written for every I going from number 1 to C, which means that for all the species, the number of moles of the species is going to be constant in the entire system, which means that the change in the number of moles of the species I in the system is 0. Now, the number of moles of any species in the system can be written as sum of the number of moles of that species in alpha region plus the sum of moles of that species in the beta region, which means that dni alpha plus dni beta is equal to 0, which means that we now have a set of relationships which basically are given here, saying that if the change in the number of moles of species I in alpha is equal to minus change in the number of moles of species I in beta, and these are all, how many relationships are these? These are actually C number of relationships, because for each I the same relation is going to hold, and these relationships will then help us in eliminating the one of the two quantities that are listed in this equation. So we then substitute these three relationships or sets of relationships in the summation of the change in the entropy of the system. Okay, so basically we see that this is an equation where there are a lot of things that are unknown. So which means that first we are going to look at how this can be substituted and how this can be substituted and how this can be substituted. So that's what we are going to do. So we now have already du alpha is equal to minus du beta, so that we substitute for du beta, and we have dv alpha is equal to minus dv beta, that we substitute for dv beta, and we have dni alpha is equal to minus dni beta, that we substitute here for dni beta, which means that we are able to see there is something common among these terms. We see that these two terms will have something common, so we can gather them together. Similarly, these two terms can be gathered and the summation terms also can be gathered. So we do that, and when we combine them, we see that the change in the entropy of the entire system is written as 1 by T alpha minus 1 by T beta into du alpha. The minus sign comes because of the minus sign here, and P alpha by T alpha minus P beta by T beta into dV alpha. Again the minus sign comes because of the minus sign here, and mu I alpha by T alpha minus mu I beta by T beta. Again the minus sign comes because the minus sign here. So this way we have written the entropy change in the entire system as an expression that goes with arbitrary changes in the internal energy, arbitrary change in the volume, and arbitrary change in the number of moles of species I in one of the two phases. Okay, we know that the sum is 0, but in one of the two phases the change in the internal energy or volume or the number of moles could be arbitrary and finite, because the atoms can always jump between the two phases alpha and beta, or the two regions alpha and beta. And we now want to see what can we comment on these three coefficients if we see that there is a condition that we can write for ds alpha. And what is that? Basically we are saying that at equilibrium entropy of the system is at a maximum. So normally if we have any process variable and the entropy is plotted, we expect that when there is a maximum, the entropy is maximum, that's when the system is at equilibrium. And if the entropy of the system is at a maximum, then from the graph we can immediately see that the change in the entropy of the system under equilibrium will be 0, which means that the slope of entropy at this point will be 0, and which also means that the expression we have written earlier is going to be 0. Okay, so which means that this entire expression has to be set to 0. And we then have a very subtle argument. We are saying that under arbitrary small changes of the internal energy of alpha and small change of the volume of alpha and small change in the species I in alpha, we want to ensure that the entropy is always going to be 0. Entropy change is always going to be 0, and this we can always guarantee. That is, it's a very subtle argument. We say that we can always guarantee if the coefficients are 0. Okay, so these coefficients which are actually highlighted, if these are 0, then we can always ensure that the right hand side is 0. So that's the reason why we say that the first coefficient of du alpha, namely 1 by T alpha minus 1 by T beta, has to be 0. The second coefficient of dV alpha, which is basically P alpha by T alpha minus P beta by T beta, has to be 0. And again the third coefficient in front of dni alpha, that is mu I alpha by T alpha minus mu I beta by T beta, has to be 0. So when these three coefficients are 0, it is guaranteed that the entropy change, this quantity, will be guaranteed to be 0, and which then guarantees that the entropy has reached a maximum, which also says that basically we have reached the equilibrium. So because of these being zeros, we have conditions that are coming out for equilibrium. Okay, so we can immediately see that the first condition is that T alpha is equal to T beta, and by substituting that in the second condition, we see that P alpha is equal to P beta, and again by substituting T alpha is equal to T beta here, we see that mu I alpha is equal to mu I beta. These are the conditions of equilibrium as we have seen from this derivation. So we write them as follows: so T alpha is equal to T beta, and we refer to this condition as the thermal equilibrium, which is also something that is very familiar to us, because we say that two bodies are at thermal equilibrium when their temperatures are equal. So it's the same thing that we are applying at a micro level, where we say that the two regions or two phases alpha and beta are at equilibrium when their temperatures are equal. Similarly, P alpha is equal to P beta, which means that they are actually having a mechanical equilibrium. So and then we write mu I alpha is equal to mu I beta, that is the chemical equilibrium for the species I, which means that we have as many as basically C number of chemical equilibrium conditions, because the species I can take value from 1 to C, because the number of species in this particular system we say that is C. The C can be 1, 2, 3 or any number that we choose to have it. So as many as those many conditions as the number of species are given. So these are the conditions of equilibrium. Now one can also look at these from Gibbs energy minimization, and again we consider a system which is given by this box, maroon box, in which there is a phase alpha and phase beta that are in contact with each other, and we then propose saying that if there is a small number of moles of species I is going to move from alpha region to the beta region, then how would the Gibbs energy change? So we want to write that change in the Gibbs energy by keeping the temperature and pressure constant. And we know from the expression for Gibbs energy that when temperature and pressure are kept constant, the only change is because of the chemical potential term. So we can see that the change in the Gibbs energy for alpha region is nothing but mu I alpha into minus delta Ni, which is the number of moles of species I taken out of the alpha region. And the change in the Gibbs energy of phase beta is mu I beta into plus delta Ni, that is the number of moles that are added to the beta region for species I. So we can then look at the total change in the Gibbs energy as the sum of these two changes, which then gives us the expression that it is mu I beta minus mu I alpha into delta Ni. Now we can see when does the Gibbs energy of the entire system go to a minimum. When the change in the Gibbs energy, the dG, is going to hit a 0. So if this were to be 0, then we have the Gibbs energy that is minimum. Otherwise the atoms or the species will continue to jump in order to reach a state where such jumps are no longer required. So which means that the equilibrium is achieved when this quantity is 0, this quantity is 0, which means that equilibrium is when mu I beta is equal to mu I alpha, and this we write for species I, and similarly we can write for every other species. So we can then say that the conditions of equilibrium for alpha and beta to coexist are temperature being equal, that is thermal equilibrium, pressure being equal, that is basically mechanical equilibrium, and chemical potentials being equal, that basically is chemical equilibrium. And here is why we are actually coming to the context of mass transfer. We are saying that the reason why species diffuse at all is because there is a disturbance in the chemical equilibrium, and in order to reach the chemical equilibrium, then the species have to move around, and that's why the mass transfer is taking place. So that is how we are motivating the reason why mass transfer has to take place at all, or diffusion has to take place at all. Okay, and from this argument you can already see that the reason why the species diffuse is to ensure that the chemical potentials are equal, which means any changes in chemical potential must be evened out, any gradients in the chemical potential must be evened out, and it is not that the concentrations have to be evened out. Okay, and we will see a subtle difference between these two in a later lesson, when we see under what circumstances you can assume that equality of chemical potentials can be assumed to be basically equality of concentrations. But by and large we can see from here that the chemical equilibrium requires that these are chemical potentials that have to be flattened out and not the concentrations. So chemical equilibrium then we can propose as basically the equality of chemical potentials, and we write that as mu I alpha is equal to mu I beta, and we write as many of those conditions as the number of constituent species. And what we do later on is by expanding the chemical potential using the same standard for all the conditions, we can actually introduce the concept that the chemical equilibrium can also be called as equality of activities. So we have first said equality of chemical potentials, but then by expanding chemical potential in terms of the activities of those species using the same standard state, we will see that it's equal to saying that the activities of the species across the two phases should be same to achieve chemical equilibrium. Okay, and so we may write that this condition is equivalent to this condition subject to using the same standard. Okay, so one may say that the chemical potentials have to be equal or activities have to be equal. They are basically saying the same thing. And we know that for ideal solutions, activity can be written as the atom fraction itself. So here I have a small correction. Activity is nothing but the atom fraction of the species I itself, and therefore we can actually write the condition of equilibrium as equality of composition, but of course that's only meant for ideal solutions. So this is where actually the difference comes. For regular solutions and for solutions which have significant deviation from ideal behavior, we see that the condition of equilibrium could be a little different. Now some remarks on the assumptions that we have made. So we have made an assumption saying that the system is inert and the interface between alpha and beta is flat. So why did we make these assumptions at all? So we don't see any reason why we have used these things at this moment. But I just want to make a remark at this point saying that there is a condition for reaction equilibrium, which is a separate condition which we will be deriving in a next lesson. And so at this moment we would like to keep the species, number of moles of the species constant, and we have used that fact in the derivation, and therefore we should say that the derivation is for inert system. If it is not an inert system, if it is a reacting system, the condition of equilibrium for a reaction is going to be different, and we will do it in a moment. And the interface between alpha and beta is flat, and the reason we say that is because the condition of equilibrium for curved interfaces is different. Particularly the mechanical equilibrium condition will have different terms on LHS and RHS, and similarly also the chemical potential terms, and the temperature equality also doesn't actually hold. You do have some change in the temperature at which the equilibrium is achieved between the two phases. So there are basically differences whenever we deviate from these conditions we have assumed. So let us just note down that these assumptions are to be kept in mind while writing the equilibrium conditions as we have written in this lesson. Some points that I would like to raise at this moment. That the interface between the two phases, if it is not flat, the conditions for equilibrium will change, and the chemical equilibrium conveys that species will move in the domain until the chemical potentials are equalized. And there is an analogy that we can draw from our familiarity with the thermal aspects, that just like the temperature is to enthalpy or heat, that is changes in temperature will lead to flow of heat. Similarly, chemical potential is to the number of moles or composition of any species. That is, change in the chemical potential across two regions will be the reason why the number of moles of any species would change or would flow from one point to another point. So in that sense, quantities like temperature or chemical potential are basically potentials which lead to flow of heat or flow of moles of a particular species, etc. And unlike thermal equilibrium, chemical equilibration will take a long time to achieve. The reason being that normally the thermal diffusivity for metallic materials is very high, whereas the chemical diffusivity is very poor. So what happens is that we may realize the thermal equilibration in an experimental scenario quite easily within a reasonable amount of time, but we may not actually end up realizing chemical equilibration completely in the entire domain. And very often we are happy if we have the equilibrium at a location, and we call it as a local equilibrium. And the time scales could be several orders of magnitude different. That is, they can be 10,000 times slower for chemical equilibration compared to the thermal equilibration. So often the chemical equilibration is realized only at the interfaces between the phases and interfaces, so it is basically a local equilibrium. So it's only a local equilibrium that we are going to basically be satisfied with. So these discussions are borrowed from the textbook titled Thermodynamics in Material Science by Robert Dehoff. It's a very nice book. I recommend all of you to go through the chapters in this book if you want to learn more about the thermodynamic aspects of equilibrium.